If I was to say the word radiation to you, what would immediately spring to mind? Well, you may think of nuclear bombs, you may think of nuclear catastrophes, accidents like Chernobyl. You may think of a bunch of tree-hugging hippies chaining themselves to fences and stuff. Well, that's certainly one way of thinking about it, but for our purposes, we're going to look at the scientific definition of radiation. And radiation is energy emitted from a source and is carried away as particles or electromagnetic waves. So if we used your heater in your home, it's a freezing cold day here in Wellington, and we have a heater, which is just a coil of electricity here. It's going to radiate out. In fact, you can get a type of heater called a radiator. It's going to radiate out thermal energy. Well, it's going to emit. It means that the heat is going to move from the heater outwards to the colder atmosphere. Okay, we wouldn't be afraid of a heater, even though it technically is radiation. If you have an X-ray, say you break a bone, X-rays are a type of radiation. In fact, they're nuclear radiation that come about from isotopes. So it needs to be an energy emitted. Emitted just means to be thrown out of, spread out from a source. The source that we're going to use of the radiation that we're going to be looking at in this video is isotopes. Now, isotopes are kind of families or types of elements with different nuclear numbers. So we could have carbon 14 or carbon 12. These are two different isotopes of carbon. All carbons have 6 protons. So why is this number different? This carbon 14 has 8 neutrons. And this carbon 12 has 6 neutrons. So these are both carbon, but they have different amounts of neutrons. And different elements have different over many number of isotopes. The particles that are going to be thrown off, or the electromagnetic waves that are going to be thrown off, are what we're going to be looking at in this video. Let's look closely at the concept of an isotope. So here I have a PhET simulation. I'll put the link in the description. And here we have a proton by itself, and let's take away the electrons. So we have just a humble proton by itself. So one proton by itself is a hydrogen nucleus. It has one proton, no neutrons. So this is hydrogen 1. If we add a neutron, we get hydrogen 2. Hydrogen 2, otherwise known as deuterium. By the way, if we remove that neutron, so it says hydrogen 1, this would be protium if you're interested in the proper word for it, but we can call it hydrogen 1 for now. So here we have hydrogen 2, deuterium, 1 proton, 1 neutron. So there is 1 proton. All hydrogens have 1 proton by definition. 1 neutron. So this is the number of nuclides in that nucleus. If we add another one, and this would be tritium, 2 neutrons, 1 proton. So it has a nuclear mass number of 3. It still has 1 proton. Okay, this is going to be so it doesn't, for want of a better word, want to be in that state. It's not sentient, so it can't it doesn't know that it doesn't want to be in that state. The reason it doesn't want to be in that state is because of energy. It wants to use as few energy, or the most efficient use of energy that it can get, and it's going to tend towards more stable. Okay, if we add another one, I don't even think that has a name, this would be extremely rare, if this exists at all in nature. But look what we have now. We have too many neutrons. And that's the main point that I want to get across here. If there are way more neutrons than there are protons, or way more protons than there are neutrons, with a bit of a proviso for that one, the atom is in an unstable state. The energy patterns, the energy system in this neutron is, in this nucleus, is going to be unstable, and it's always going to move towards a more stable state. Okay, so let's add neutrons and protons together. So we have helium-4. So the helium-4 is going to be important for us for a reason that's going to become apparent a little bit later on. So helium-4 has 2 neutrons, 2 protons. The nucleus, of course we don't care about the electrons at this point. Notice this is more stable. This is at a stable state. It's just going to stay in that state. If we keep adding neutrons, it's going to be very, very, very unstable. And we're going to get to the concept of half-life in a second. So it wants to be helium-4. How is it going to do that? It's going to just get rid of one of those neutrons. And that neutron leaving is going to be a form of radiation that we're not going to cover today. But it loses one, becomes stable. That's the main point I want to get across. By now, you should be familiar with this thing here, the periodic table. This is an interactive periodic table. Again, I'll leave the link. So this is the Royal Society of Chemistry. So for each element here, we have helium, helium-1. So all heliums have 1 proton. So it's in the first group, the first column here. It has 1 proton and however many numbers of neutrons. If we add another proton to that, we have helium. Okay, if we add another proton, we get lithium. Another one, we get beryllium, boron, carbon, nitrogen, oxygen, etc., all the way up here to oganesson, which has an unknown density. This wouldn't exist naturally on Earth in nature. This would probably only exist for fleeting moments, like very, very, very short periods of time in labs. And then again, it has, because that has no real use for us that we know of yet. I mean, you may be watching this in 50 years' time and this will be very, very important, but currently there's no use for this. Down here we have uranium. Uranium's going to be important a little bit later on, but we have the key isotopes here. So uranium has an isotope of 230. Oh, here we go. Sorry about that. Uranium 234, 235, and 238. So those are the most abundant uranium isotopes that there are. Okay, you should be familiar with that. For us, for nuclear physics, we need to use this table here, and you will see this table appear an awful lot. So in this is our periodic table. We have hydrogen. Here we have all of the known isotopes that have been developed over time. Now, there is sort of a bit of argument about how many have been discovered or isolated. It ranges anywhere from 3,300 all the way up to 4,000, depending on how you define an isotope. We're certainly not going to be worried about that for now. Okay, so here we have hydrogen 1, protium. So that is one of the isotopes. If we add a neutron to that, it's deuterium. Now down here, we have the dot. Let's zoom in a little bit. This is on a black square, and this is colloquially called the valley of stability. And what's going to happen is that these elements are going to decay until they are on that valley of stability. When they're on that valley of stability, they will stay there because by definition, they are stable. If we add another proton, okay, we have helium-3. Helium-3 is stable. Let's zoom in even more. Okay, can we have helium without a neutron? Yes, but it doesn't exist. And the reason it doesn't exist is beyond the scope of this course, but it's because it would break some quantum mechanics laws. It would break Pauli's laws. It would break Schrodinger's laws as well. So helium can only exist in these isotopes. So this is a neutron, this is hydrogen, helium, lithium, beryllium, boron, carbon, etc. Okay, let's have a look at this table a bit closer. So on this axis here, we have the number of neutrons. So and I think this is actually the opposite of the one that we were just looking at. So this is the neutrons, and this is the protons. So hydrogen is here, helium, lithium, beryllium. You have uranium here, which is 92 protons, and we see something interesting. As we get heavier and go to the laser pointer, as we get heavier and heavier, the number of neutrons starts to outnumber the number of protons by a lot. The reason for this we're not going to cover either, but it's because of Pauli exclusion, and it just would break energy rules to have more protons than neutrons at this mass. If you're doing university, you'll cover that, but this is only a level 2 NCEA course. Okay, so it kind of bows outwards and upwards. So by the time we get to uranium, we could have uranium-235, even though uranium only has 92 protons. So we'll therefore have 143 neutrons. And there is, of course, uranium-238, which also has 92 protons by definition. So that's going to have, 146 neutrons. Here we have the valley of stability. So it kind of goes there like this. There are some gaps there, by the way, that we're not going to cover why there are little gaps. So it's a very, very thin window of opportunity here. And then it kind of stops at 82. So there is nothing above 82 and onwards which is stable. So everything from here is going to be unstable. Okay. Now, because it wants to get to that valley of stability, if it is, say, for example, here, okay, so this would be element, that looks like about element 58 or something. It has too many neutrons. It wants to get rid of those neutrons to move to the valley of stability. To do that, it's going to get rid of neutrons. Okay. Here on the other side, we have in the orange bit here, we have too many protons, not enough neutrons. So it's going to be unstable. The energy is going to be all out of whack, and it's going to really not like being there. So here, there are too many too many protons. Up here, there is just too much energy. Too much energy. Okay. If there are too many neutrons, it's going to be blue, which means we're going to have beta decay. So beta decay occurs when there are too many neutrons. So we're going to define what these things are. If it is beta plus, there are too many protons. If there is alpha decay, it means there is too much energy and really just too much mass. Mass is proportional to the amount of energy through E equals mc squared. We could potentially have spontaneous fission, spontaneous release of protons down here, which we kind of did before. Spontaneous ejection of neutrons. There are, if you look closely, there are a few down here. We're not going to worry about that, okay? All that we're going to worry about is alpha plus, alpha negative, beta plus, beta negative, alpha, and another type of decay called gamma decay, which is sort of a different type of radiation. Okay, so let's look at exactly what these things are. Let's look at alpha decay first. So when alpha decay, when we have alpha decay, we have alpha radiation, which means that the atom will throw off. Right, let's look at iridium-165. Let's look at alpha decay first. So alpha decay will occur. When will it occur? Well, we need to work out exactly where this iridium-165 is, and we can get rid of the electron cloud. We don't really care about the electrons. This, by the way, this kind of looks static. It looks like it's kind of not moving. There are all sorts of forces. There is a strong nuclear force. There is a weak nuclear force. There's electromagnetic forces in here, which are all kind of competing and fighting with each other. Some of them want to break this nucleus apart. Some of them want to keep it together. Some of them want to change it. Some of them want to keep it as it is. There is kind of organized chaos or madness going on in this nucleus, but we're not going to worry about that just right now. So iridium-165, so it's defined as having 165 nuclides in it, which means it has 77 protons. All iridium has 77 protons and has 88 neutrons. So we're seeing this trend where there's more neutrons as they get heavier and heavier. There's more neutrons than protons. Okay, let's have a look to see where that would be in our interactive chart. So I've got iridium-165 here, and we can ignore the electrons. If you're interested, this is what it looks like. There's no known uses for this isotope. So we have iridium here, 165, and it's this little red dot here. Now I'm going to zoom in a little bit. So all of these are, if we zoom way in, so all of these are the iridiums. It wants to be down here. Now there's two things here. There's too many protons. It wants to either move down towards the valley of stability here, across here to the valley of stability, or some combination here. Which way is it going to do it? It's on the yellow, which means it's probably going to be an alpha decay. Okay, so we have alpha decay ready. What is alpha decay? Alpha decay is a helium atom, a very, very high energy helium atom, a helium nucleus, I should say, but a helium nucleus, and a helium-4 nucleus to be more exact, which has 2 protons, 2 neutrons. So to get rid of those protons, it's going to spit them out. So now we lose 2 protons, we lose 2 neutrons. This is no longer iridium. This is rhenium 161. I don't know if that has any use. We can find out. So we lose 2 protons, we lose 2 neutrons. There's no known uses for this isotope. That's what it looks like if you're interested. This is radioactive. Radioactive means it has a tendency that it wants to decay and emit radiation. Remember, radiation is the emittance of energy from a source, and it's going to emit that energy in the form of particle. So again, it's still got too many protons. Too many protons. So what does it do? It's going to spit them out again. It's going to spit out another helium nucleus. So we lose 2 protons, we lose 2 neutrons, and now we have tantalum 157. I don't know if that has any kind of use. Again, we're going to ignore the proton emission here. We could just lose protons, but we're not going to. Okay, well, it's going to undergo another alpha decay. So it spits out another alpha decay. And this is getting more and more stable. So if you notice that this is moving up here in terms of stability. So now it is lutetium 153. Now we have 2 courses of action that are available to us. We're not going to use beta plus decay. We're going to have alpha decay again. So again, there's too many protons. It wants to get rid of those protons. It's going to spit 2 of the protons out because it wants to get rid of those protons more than the neutrons. So it's going to spit those out. Now it's unstable, but now alpha decay is not available to us. We're not going to get into the reasons why it's not available to us. Suffice to say that thallium now is still unstable, but less unstable than it was before. I mean, we started way down here and now we're here. So here is thulium 149. It's still here. It wants to get, if you have a look, it even gives us a little line here. It wants to get to this area of stability here. It doesn't have alpha decay available to us now. It has a little bit down here. So it's going to want to lose these protons. So it can't do alpha decay. How is it going to get rid of those protons? Well, it's going to have beta decay. And beta decay is when we have a proton becomes a neutron and emits some energy. It emits energy in the form of a positron, which is a positively charged electron. We're not going to worry about that just right at the moment, but it is going to emit an electron. So what's going to happen? The protons here are going to go down by 1. This is going to stay the same because we still have the same number of protons plus neutrons. It's just now we have 1 more neutron, 1 less proton. So let's do an alpha beta plus decay. It's going to emit that positron. So now it is erbium 149, still has the same number of protons plus neutrons, but it's lost proton. So it is now no longer the element that it was before. But again, it's still too many protons. It doesn't have alpha decay available to it. So it spits out another positron. It converts a proton into a neutron. Again, there's too many protons and not enough neutrons. And now it is kind of more unstable. It is kind of less unstable. It's still unstable, meaning it's radioactive. So it's going to decay again. And if you see this moved across, it spits out the positron. Now there is one less proton. So now it is dysprosium. I've hardly ever heard of most of these. 149, again, protons plus neutrons equals 149. It's still unstable. It's going to spit out another positron. It's going to convert a proton into a neutron. The difference is going to be spat out in a high energy positron in the form of beta radiation. And now it's terbium 149. Protons plus neutrons still equals 149, but now it has 65. Now there are one of two paths available to it. It can either do alpha decay or beta decay. Let's do alpha decay again. So now it's still unstable. There's still too many protons than neutrons, but it's becoming less and less unstable and more stable. Now it's europium 145. And we got rid of 2 neutrons and 2 protons. So there's a total of 145. And now we're going to have beta decay again. Samarium 145. Let's decay it again. It's still unstable. Promethium 145 again. Now there's alpha decay available to us. So it's released in the form of alpha radiation. And now it's stable. Dinium 141. It's stable. When it's stable, there's no available decays available to us. So let's have a look at on our elements chart. And now we see praseodymium 141 with its 59 protons and 82 neutrons is on a black square. It's in the valley of stability, and it's where it's going to stay because it's stable. So it's kind of falling into that valley. So we started way up here, and it's kind of moved down here through, I lost count, probably about 9 or 10 decays till it reached that point. Okay, let's use it in aircraft parts. It's also used in permanent magnets, studio lighting and projection, welders goggles. Great. Okay, fantastic. Let's look at the other end of the spectrum. Let's look at this pink bit here now where there's too many neutrons. So here we have carbon 14 now. So all carbons have 6 protons. This one has 8 neutrons. There's too many. Let's get rid of the electron cloud. There's too many neutrons. It's unstable. It's not really all that unstable, but it's still unstable. So this is going to decay. It's going to radiate, emit something to get to that value of stability that it wants to be at. So now there's too many neutrons. So it kind of, the grey ones, and it converts it into a proton. And the energy difference is a beta particle, which is an electron, a very, very highly energized electron. There's going to be quite a big energy change in the nucleus. That energy has to go somewhere, and it's going to be spat out in the form of a high energy electron or a beta particle. This is beta negative. Now, how do you remember which one is which? The negative bit means that it spits out a negative electron. Beta positive, it spits out a positron, a positive. So let's have a look at it. The beta 14, it's spat out there. The neutron becomes a proton. So it changes from carbon to nitrogen, decays into nitrogen 14 with 7 neutrons, 7 protons, and everyone is happy. It has a infinite half-life, which means it's not going to decay at all, ever. And this is older than the age of the universe. Let's have a look at another example. Here we have fluorine 21. It's fluorine because it's by itself, not fluoride. It has 12 neutrons, 9 protons. All fluorine has 9 protons. Now there's too many neutrons. It's not heavy enough to have an excess amount of neutrons. So it wants to get rid of those neutrons, or at least change the ratio. How's it going to do that? I can't really spit out a neutron. It doesn't have enough energy. So it's going to be beta negative decay. So it's going to take one of those neutrons and it's going to convert into a proton via the weak nuclear force. The difference is going to be spat out in the form of a high energy electron, a beta particle. By the way, the beta particle comes from the nucleus. It does not interact with the electrons that are already in a cloud around there. So we have the electrons here, and when we eject an electron, it's going to come from the nucleus, not from the existing electrons. Now it's stable. So we gained a proton, we lost a neutron, now we have neon. And we know this is really, really stable. It's radioactively stable. It's also chemically stable. It's a noble gas. So it's going to be in that valley of stability there. All right, so thus far we've covered 3 types of radioactive decay causing radiation. We've covered beta positive decay. Beta positive decay is when there's too many protons. We've done beta negative decay or beta minus decay, too many neutrons. We've done alpha decay, there's just too many things in there to start with, usually protons. Okay, what about the other form of radiation, which is gamma radiation? And by the way, alpha, beta, and gamma are the first 3 letters of the Greek alphabet. They're called alpha, beta, and gamma because the person who discovered them, guess who? Our old mate Lord Rutherford discovered that one first, that one second, although he didn't differentiate between alpha positive and negative, and he discovered that one third. So he just called this one alpha, beta, and gamma. All right, notice that gamma is not here. What is gamma decay or gamma radiation? We have gamma radiation when there is too much energy in the nucleus. And this usually have gamma radiation after the after alpha radiation up here, the heavier atoms. After alpha decay, when there is still an excess, there's too much energy in the nucleus. So remember, we get back to our definition of radiation. So radiation is energy emitted from a source and carried away as particles, which is alpha or beta, or electromagnetic waves. And gamma is an electromagnetic wave, kind of like light or X-rays, much, much, much more energetic. So if we have some element and it has a gamma decay, let's say that we have, I can't remember which way we're supposed to do that, and it has decay, it's going to have the same number of the mass number, plus it's going to have 0, 0. It's going to emit a gamma radiation, and it's going to get rid of, it's going to sort of boil off, I've heard it described, the energy that's in the nucleus. So if we have our kind of nucleus here, and there's too much energy, there's energy all over the place here. There's cats living with dogs. It's all madness. It's going to emit in the form of electromagnetic wave, an alpha particle. Although we don't really think of a particle, we kind of think of it as a wave. Okay? It doesn't affect the nuclear ratio neutrons to protons, but it does affect the energy. It does it for a reason. It's not going to have excess energy in the nucleus if it doesn't need it. That energy has to go somewhere, and it's going to be emitted in the form of that electromagnetic wave. All right. Next thing we need to cover is really how kind of dangerous, or how penetrating these forms of radiation are. First thing we're going to look at is the alpha radiation. And alpha radiation can be stopped by the skin. It can be stopped by paper, probably cardboard. Okay, it's not going to get very far. If we have an alpha particle, it's going to move along until it hits this barrier, and it's not going to get through it. Beta radiation is going to go through that paper, and it's going to be stopped probably by a metal. Okay. Gamma radiation is going to be more penetrating. It's going to go straight through that paper, through that skin, through that metal. If we want to stop it, we're going to have quite a bit of either lead or concrete. And even then, it's not going to be totally effective. It's going to go through those. Okay, so the question is, which is most dangerous? Well, the danger really comes from its ability to ionize atoms. So ionize means to strip the electrons from atoms. So if we have the nucleus, and we have the electrons floating around here in a cloud, the ionizing energy, it's going to sort of knock one of those off and sort of push it out into the world. Why is that dangerous? Well, it's dangerous with biological entities like plants or animals, because our DNA and our biological chemistry relies on the bonds that are formed in those atoms. So if we have atoms of carbon that don't have enough electrons, they're not going to bond. So the DNA is going to break down, and the biological matter is not going to be able to bond with other biological atoms to form the molecules that's required for life. Okay, so you would think that gamma radiation is the most ionizing. In fact, alpha radiation is the most ionizing. Beta radiation is the next most ionizing. Gamma radiation for us is the least. It will still ionize though. Still dangerous. Notice here the difference though, that this is the least ionizing, but it's the hardest to stop. Alpha radiation is the most ionizing, but it's the easiest to stop. That does not mean that it's not dangerous. You do not want that getting in your body in the form of your food or your water, or in your lungs through the air. If it gets in, it's going to stay in, and it's going to ionize. So even though it won't go through skin or paper, that's okay if it's outside your body, but as soon as it's inside your body, it's going to be dangerous. So there is a kind of trade-off here. You can deal with alpha radiation in a lab. You're most likely to come across it, but you're definitely not going to want that inside your body. So here's a little sim that I've had made up. Here we have an alpha particle. We're going to fire it, and it's going to be stopped. It's going to be absorbed by paper, stopped by paper as far as we're concerned. It's large, it's slow. I mean, it's moving very, very, very fast, but in relative terms, it's moving slowly, and they will lose their energy over a few centimeters of air or on the surface of some barrier. Beta particle, let's move this up. We're going to fire it off. It's going to go through that paper, and it's going to be stopped by aluminium, a metal. They're much smaller and faster than alpha particles because, remember, an alpha particle and is a helium nucleus. A beta particle is a positron or an electron, highly energized positron or electron. So it's going to go through, but it's going to lose a lot of its energy, and it's going to be less ionizing. Gamma radiation, if we fire a gamma ray, it's just going to go. It's just going to go right through them. Okay? So it has no mass or charge, and it will not interact much with matter. Doesn't mean that it's not benign. It's not dangerous in any way, because it just will keep going and going and going. But it's less ionizing. Gamma radiation is quite dangerous in nuclear blasts because there's just a lot of it. In a nuclear blast, there is all sorts of radiation given off. There is X-rays. There are photons given off. There's this thermal radiation given off, and gamma radiation as well. The next thing we need to cover is deflection of radiation. So here we have a magnetic field. So this is coming out of the page. So the magnetic flux is coming towards us. And here we have a source of radiation. If we fire an alpha particle, it's going to move in one direction. If we fire a beta negative, it's going to curve away very, very sharply in that direction. A beta positive, a beta plus, it's going to curve away the other direction. The gamma, it's going to just keep on trucking. It's going to thumb its nose at that magnetic field, and it's going to keep going. Okay, so let's do that again. Alpha, kind of this lazy curve downwards with respect to the magnetic field. Beta negative, the other way. Beta positive, the other way, and more pronounced than the alpha particle. And the gamma particle just goes straight through. It doesn't care. Fire them all at one go. It's going to look like that. You may be asked that in your assessment. This is how we can tell the difference between alpha and beta radiation. So, like I said before, Rutherford discovered beta radiation. He discovered, I don't know whether he discovered alpha, positive or negative later on, but that's how they are distinguished, because negative goes that way, positive goes that way. They're kind of mirror images of each other. That way, that way. Okay. So now we get to the sort of mathsy bit, and it's the concept of a half-life. Half-life is the concept which was first discovered by our Lord and Saviour, Lord Rutherford of Nelson, and a half-life of radioactive isotope is the time it takes. So it's going to be time. So, I mean, the SI unit for time is seconds. Sometimes though, it doesn't make sense to have it in seconds. We have it in years. It takes the number of undecayed nuclei or the activity of the sample to decrease to half of its original value. Okay, so if the half-life, which is T subscript half, So if the half-life is, say, 10 seconds, and we start with 300 nuclei, after 10 seconds, we're going to have 150. 10 seconds later, we're going to have 75. 10 seconds after that, we're going to have, well, whatever half of 75 is. 37.5, because we can't have half nuclei, so we're going to say 38. So it's going to reduce and reduce and reduce. It's not only the amount, but it's the amount of activity as well, or half. This was one of the things that got Rutherford his Nobel Prize. And in fact, if we have a look at the New Zealand $100 note, we can see that in here, there is a graph of half-life. So we start there and it halves every half-life. That is the half-life graph. It's this is his Nobel Prize. This is the man himself, Lord Rutherford of Nelson, and there is the half-life graph. There is another one that goes there like that, which is related to that, but this is the one that we're worried about here. Okay. So here I've got GeoGebra to do the equation. So we see the half-life here. We can ignore this because it sort of starts there. So this is the amount of the nuclei that we start with. And each one of these is going to be one of the half-lives. So if you have a look at the graph here, yep, it's the same graph that's on our $100 note. All right, let's have a look at the equation itself that we're going to be dealing with. So the equation that we're going to be dealing with, there's a couple of ways of showing it, but the way that I'm going to show it is the sort of the calculus way that level 2 students can understand. So it's the number of nuclei at some given time is going to be equal to n0 brackets half to the power of t divided by t subscript half. Okay, so it looks a bit daunting, but let's break it down to what these are. So this is the number of nuclei which are left at some time or after some time t. Okay. N naught, you can think of this as n naught is the initial number of nuclei. So, I mean, and theoretically here, it's the number of nuclei. Often this can kind of be mass as well, but it's really, it should be the number of nuclei rather than kilograms. But if we put mass there, we're not going to go far wrong. Half is, of course, the fact that it's half-life. T here is going to be the time elapsed since n0, since we had n0, and t subscript half is the half-life of an element. Well, an element, really an isotope. Okay, so let's kind of break this down. Let's look at one of the most important ones, and that is carbon-14. So carbon-14 is the second most abundant isotope of carbon. I think carbon-13, yeah, I think carbon-14 would be there, and carbon-12 is by far the most abundant isotope of carbon. So carbon-14 is unstable, and we did this before, so it's going to decay. Carbon-12 is very stable. It's not going to decay at all. So carbon-14, what happens to carbon-14? Let's do it again. Carbon-14 is unstable. It has too many neutrons, so it wants to lose that in the form of beta decay. So we're going to look at what the half-life is. So the half-life is 1.8 times 10 to the 11 seconds. Okay, so it's given to us in seconds. By the way, each rung here is 1,000 times greater than the one before. This is not a linear scale. Carbon-14, it wants to decay. So after one half-life, half of it has undergone beta minus decay. The neutrons have been converted into protons, and it's emitted a high energy electron, a beta particle. Now it's no longer carbon, it's nitrogen. It's got 7 neutrons, 7 protons. Everyone is happy. We're all fantastic. The half-life is 0, so it is absolutely stable. But let's work out why this is important. When biological matter dies, the carbon-14 starts decaying. So if we know the ratio of carbon-12 to carbon-14, and we know the half-life of carbon-14, remember we were given it before, it's 1.8 times 10 to the 11 seconds. We can therefore, if we know the ratio, we can work out how old something is which used to be alive. And this is carbon dating. Okay, so let's convert that into years. Well, 1.8 times 10 to the 11 seconds is 5,704 average Gregorian years. Quite a long time. So we can fairly accurately, remember this is a very, very predictable rate of decay, even though we don't know which atoms are going to decay. As a whole, we can pretty accurately work out the decay of all of the atoms on average. So we can use that to date things. So let's do that now. All right, we're told that a piece of ancient wood is found to have only 25% of the carbon-14 activity expected in a living tree. So it's a little bit more complicated than that. They look at the ratio of carbon-14 to carbon-12. But let's go with this. So we're told that there is 25% left. How old is this piece of wood? Well, at time t equals 0, there was 100%. After one half-life, there would have been 50%, and after 2 half-lives, there would be 25%. So this piece of wood is 2 half-lives old, carbon-14 half-lives. And we know that carbon-14 has a half-life of 5,704 years. I think this is not quite right. I think it's a little tiny bit more than that. I think it's 3,730 something. So that's rounded a little bit. Okay, so our piece of wood is going to be twice as old as that. So the age, therefore, is going to be 2 times 5,704 years. We're not going to do it in seconds. It's not going to make much sense to do it in seconds because it's not going to be that exact. So that's going to be what, 11,400 odd years old. Last off, we have radioactive isotope with an initial activity of 800 counts per minute. So maybe there's the Geiger counter and it's clicking away at 800 clicks per minute. After 18 hours, this has fallen to 100 counts per minute. Now, there's two ways of doing this. There's the hard way and the easy way. We could put in these values because we want to calculate the half-life, put these values in and use algebra to find that. Or we could kind of intuitively do it half-life by half-life. So when we start off at time 0, there are 800 clicks per minute. And then after one half-life, there are going to be 400. After two half-lives, there's going to be 200. And after three half-lives, excuse me, there's going to be 100, which is what we're going to be looking for. So we've kind of lucked out. If we wanted to solve this one, we're going to need logarithms. So it's after three half-lives. 18 hours divided by 3 is, of course, 6 hours. I wouldn't do it in seconds because they give it to you in terms of hours, even though this is 800 clicks per minute. So this here is kind of a red herring. And that's that. No doubt I've probably misspoken a couple of times, called nucleides, nucleotides or something like that. Let me know in the comments. So I always enjoy listening to your comments. Next time we do relativity. So we go from Rutherford to Einstein.
What about radiation?
Obviously down here it's nothing, but in the reactor building I'm being told 3.6 Röntgen per hour.
Well, that's not great, but it's not horrifying.
Not at all.